Anastasia Volovich, and the title is Cluster Algebras, Landau Singularities and Scattering Amplitudes.
Okay, so first of all, it's great to be here again. Thank you so much for inviting me. So what I'm going to try to do today, I'm going to try to tell you a little bit about some interesting mathematical structures that arise in quantum field theories, and in particular in the studies of scattering amplitudes in quantum field theories. So this is some work that's based on a series of papers with our Mark Spradlin, two students from Brown, Igor Plilna and Stefan Stanojevich, and our postdoc, James Stankovic. Okay, so let me start with a plan. So I'm going to start with a quick introduction of what objects are we going to study and why they are of interest. Then I'm going to try to explain to you very hand-wavy the so-called bootstrap program for computing scattering amplitudes. So one of the inputs in that program is something called symbol alphabet, and I'm going to explain what that is. And the question would be, and that's sort of an input that goes into that program, and then one uses various physical and mathematical properties to determine those amplitudes. And the question will be, how could this input be determined? And there'll be two parts of the talk. So first of all, there'll be I'll explain the connection between cluster algebra and the symbol alphabet. And secondly, so that's something very well known in mathematics. And then towards the end, I'll explain the connection between the symbol alphabet and Landau singularities. Okay. All right, so let me start. So the theory that we are interested in studying is called planar n equals to 4 super Yang-Mills theory. And there are at least three reasons why we're interested in this theory. So number one, it's a quantum field theory which describes quote-unquote real-world particle interactions. So it's the simplest theory, it's a simplest quantum field theory with the simplest possible scattering amplitudes. However, when we do the computations in this theory, we try to, and we compute, we look for structures, and we develop techniques in this theory. Of course, one of the goals is to extend those techniques to more realistic theories, such as QCD and the standard models. And indeed, many of the techniques that were developed have been applied to more realistic theories. So that's number one. Number two, reason for studying n equals to 4 Yang-Mills theory. So it's a string theory via ADS-CFT. So learning about n equals to 4 Yang-Mills theory teaches us about quantum gravity. And finally, it is an apparently solvable or integrable theory, which is a not trivial statement for a four-dimensional quantum field theory. So certain quantities in this theory have been computed to all orders in the coupling constant. So again, hopefully that's enough of the motivation why we study n equals to 4 Yang-Mills theory. Now, the objects that we are interested in, so various people, are computing various things in this theory, first of all. Some people are computing anomalous dimensions, correlation functions. So my talk is going to be about scattering amplitudes in this theory. So scattering amplitudes in quantum field theory are characterized by three numbers. So first of all is number n, which is number of points. So when some particles come in and some particles come out. So you have 2 to 4 scattering, that would be 6-point amplitude. So they're usually computing using Feynman diagrams. So this is a Feynman diagram for a 6-point amplitude. So secondly, they're characterized by number L, that's the number of loops. So that is a 5-loop amplitude. You see 1, 2, 3, 4, 5. And then there's a number k, which is the degree of non-MHV. But for most of the talk, we don't need to worry about this k. Most of my talk will be k equals 0, although I'll have something to say about high k's. Okay, so here I kind of outline the status of this computation in this theory. So so normally one starts at tree-level amplitudes. So what is known? So this is like a summary slide of what's known in this theory. So at tree-level and one-loop amplitudes, they've been known for about 20 years. So the pioneers here are Ben Dixon and Kosover, and they're known for 0 and 1 loops for all n and all k. Now, if we start moving, increasing the number of loop order, so here, as you see, 2, 3, 4, 5, etc. So at 2 loops, we know all endpoint MHV amplitudes. So the formula first was written about 7 years ago by Simon Caron-Huot, so 2011. And if we also here included the K, so if we go to NMHV, so MHV is an amplitude with 2 negative helicity gluons and any number of pluses. NMHV is 3 negative and all pluses. So obviously for 6 points, all you can have is MHV or NMHV. So these are also known for some 6 and 7 NMHV amplitudes. Now if you start going further, so there has been work, but mostly this has been pushed by Lance Dixon and his collaborators. So, and these computations have been done using this bootstrap program. So if you move to, 3 loops, you see there are, this dot doesn't go, yeah. Can you see the dot or no? This is like
where is the dot? Where is supposed to see it?
At 6 and 7, is there like a normal point or something? Like a basics.
Finger is the best point.
Finger, yeah, but that's not the. There's no like this.
Oh, wait.
Now it's. Maybe if I use.
Yeah.
Oh yeah, maybe that's better.
It's the best point.
Okay. Yeah. No. But the problem is, look at it. Yeah. Okay. So now if we go to 3 loops, you see it's 6 and 7 MHV. Then if we go further, starting at 4, only 6 points MHV are known. Okay? And because of various properties of this theory, so all 4 and 5 points are known to all loops. So the first non-trivial ones would be starting at 6 points. Okay? Okay, so that's the status of these computations. So why can't we just, since it's such a nice theory, why can't we just sit and write down, so now it disappeared. Why can't we just sit down and write down this, these amplitudes? So what are some of the difficulties? So how do we compute these in quantum field theories? So in quantum field theory textbook, the way it is done, the computation is split in 2 parts. So first, you have to write down an integrand that you have to evaluate. So for example, on that slide, schematically is a picture of a 4.7 loop integrand. And then what you need to do, you need to integrate this. So there are some loop momenta, and then you have to do this integral. So first you draw the set of all possible integrands, and then the hard problem is to actually integrate. So once you integrate, you get some basically, normally if you do it like this way, you start getting very, very complicated functions. So the statement here is, I should have put references. So the integrands are known. So the top, so for plane n equals 4, this part is known through the work of Nimar Kani Hamed and others. These integrals are known for all loops and all n. So if you want to, if you want an integrand, you can just open a paper and you see it. Now, in certain variables, that again, I will come to that. But actually, the difficulty is actually doing this integrand. And as you've seen, there are many cases that are known. So what's the goal here? So we're looking for new tools to make this calculation possible. Now, you can always ask, why would you care about some 17 loop and 50 point amplitude? Well, because usually the way this field works is that doing more computations have been crucial for identifying hidden structures in these amplitudes. So some new symmetries have been, by analyzing properties of high loop amplitudes, some interesting new symmetries have been identified, such as dual conformal symmetries, Youngian symmetry, and others. So we are always looking for new tools and new mathematical structures in these objects. Okay, so as I mentioned, so you see, so that's, this is with methods of quantum field theory. Now, let me tell you a little bit about the bootstrap program. So as you saw on this previous slide, Dixon and collaborators were able to go to quite high loop orders. And how are these computations done? Well, it turns out that the modern approaches to doing this, they avoid the knowledge of integrands completely. So that's something that is easy to explain. So what is the point here? Well, the point is the following. So we, instead of evaluating these integrals, so this is an integral for 6.5 loop amplitude, we think of these amplitudes as particular functions on certain geometrical data. So there are two things we need to know. We need to know the set of geometrical data and the set of functions. And then we can use a set of mathematical and physical properties to determine these functions directly. Okay? So let me now explain to you. So we forget about quantum field theory, integrals. Let me try to tell you what are the functions we are looking for and what are their functions of. What are the arguments of these functions? Okay, I'm going to do this with an example. So the way we're going to think about this is a function of a geometrical data. Now, is this formula visible at all? You can see it? So, for example, take 2-loop 6-point amplitude. An example of a function of this amplitude would be a transcendental function, which I'll explain, remind you on the next slide, of some cross ratio. So we're looking for some functions of some arguments. Now, let me explain to you what are the functions. So because it's a particular theory, planar inequals for Young-Mills theory, it is conjectured that these functions are believed to have a uniform transcendentality. So what is a transcendentality? So for example, log has a transcendentality 1. Pi has a transcendentality 1. So it is believed that L loops, we deal with 2L transcendentality. So for example, the 2-loop answer that I had on the previous page is L equals to 2. 2L is 4. So that's the 4 that you see here. Okay? So more generally, so we know the log. The more general functions are PolyLog functions. So Li1 is a log, and Li2 is defined by a recursion formula like this, and Lik is defined by a recursion formula like that. And there are also generalized PolyLog functions. They're called also Goncharov PolyLog functions. That's when these polylogs have certain weights. So that instead of ones, so you see here logs have 0 or 1s, you can put some parameters a's. Okay, so that's a set of functions that we talk about. Now, what are the functions of? Okay, so so normally when we compute scattering amplitudes in field theory, the amplitudes are functions of momenta. P1, P2, Pn. Now, it is known that there is a map. So there is a map between the null vectors, the momentum p squares to 0, in Minkowski space, subject to momentum conservation, and a set of n vectors in P3. Something called, there's a map that explicitly, maybe George, if you want to write that map explicitly in terms of momenta, so P1, P2, P6, so you form these U's, and so there's to each point each point in the momentum space you identify a line. But the thing to remember for you maybe is just that, so we have this amplitude and we have n vectors in P3. Okay, so these functions are defined on the configurations of endpoints in P3. Okay, okay. So given these, given these z's, so for example, you can, out of these vectors, you can build, you can take a determinant, and so everywhere you will see these brackets, I, j, k, l. And these are the determinants of zi, zj, zk, zl. Okay? And because of various properties of scattering amplitude, which again I'm omitting, normally you take some cross ratios of these. So if you, yeah.
This is the relation for complexified momentum?
Yeah. Right. That's right. So, good. So, hopefully, I roughly explained to you the idea. So, we have to, so we kind of understand what all the functions are, and we kind of know how to think about these arguments.
So, is the hard part getting the highest transcendentality, or are the products of lower transcendentality sort of easy to find? I mean, or is it all?
Yeah, there are two parts. One hard part is to figuring out what these arguments are. And then the second hard part is classifying all set of functions. So start after weights, so it's known that up to weight 4, so that's 2 loops, they're only classical polylogs. Starting at high loops, at 3 loops, these more complicated, these contour of polylogs start appearing. For example,
people talk about elliptic functions.
Yeah, there's also a lot of work has been done recently, in fact, by Claude Dour and others, because it is believed that at certain 8.3 loops, there'll be more complicated functions appearing because the integrals have them. So if they evaluated, in fact, I'm still at low loop and low end, but there's been a series of papers within the past 2 months. Generalizing these two elliptic. So everything I have to say today is going to be only about the PolyLog functions. Right. However, I should also mention, even though these are elliptic, the methods, the cluster, the arguments would be still valid for the elliptic. So that still is useful.
And the bootstrap idea, the hope is that this will apply.
The hope is that it will.
Of everything?
Yes, that's the hope. But it's steps, yeah. So right now, I think most notably, Claude Dour is working, a series of papers of these elliptic. So the symbol that I will mention, for example, recently has been generalized to that case. Yeah. But indeed, the way they do it is by integrals. It could be, to me, I haven't seen integral sum, and there's no elliptic at the end, so nobody knows. So,
how is it? You said that at some point elliptic versions appear, and do you know why there is this transition line? Because those polylogs is a kind of genus 0 objects, and then elliptic are genus 1 objects. What changes? Do we know how this genus appears?
Well, we know at what L and N they start appearing just by drawing the integral and say, okay, this integral, if you do it, if take the Stowe integral, it is elliptic function. So that's I think the way they do it. Yeah.
But you cannot expand elliptic functions in PolyLog?
Yeah, like some infinite sums, maybe. Yeah, some infinite sums. Yeah. So I personally have not worked on this, but there's serious. Jake Bugelli also, for example, working. Several people in this field are doing this. Yeah.
Because then, if they're truly independent, then as Anton is saying, then maybe you'll have something to use too in this thing.
Yeah, maybe, and maybe they will also yeah, it's very unless somebody really computes, it's very difficult to make speculations.
Partly experimental.
Yeah, a lot of it is experimental. In fact, this whole a lot of that's yeah. Mm-hmm. Any other? Yes. Yeah, but okay. Good. So these. Okay, so symbol now. Okay, so far I've explained to you that the way we think of an amplitude is a function of geometric data. A useful object that we're going to study and that's been proven to be very useful in this field is called symbol of this PolyLog functions, and this is a notion that's been introduced by Goncharov a while back, and it's been very useful in this field. So what is the symbol of this transcendental function? So let me give you two examples. Some of you might have heard this. So let me just give an example. So take a function log. Okay. So first of all, symbol is a map of the function to an element of a tensor product. Okay. Now, so degree k, transcendental function degree k maps to k tensor product. So for example, let's take a log. So a symbol of a log R is R. Okay, definition. So any transcendental the class of function that we are looking at could be written in this form. If you take the differential of a weight k, it could be written as a weight k minus 1 function d log of some other argument. So by definition, so symbol now that I gave you this, symbol could be defined recursively. Symbol of this is a symbol of the previous function times the argument of R. So it's a little smarter way than just doing the derivative. So for example, if you remember our definition of Li2 that was on previous slide right here, so you take, so suppose k is 2, d Li k is Li1 d log, right? But Li1 is minus log 1 minus z, so thus the symbol of this is minus 1 minus R tensor R. Okay? And so for example, for the function at hand, for this one, since I had Li4 here, the symbol is minus 1 minus x tensor x tensor x tensor x. And that also quickly follows from the definition. So the reason there are various reasons why it's useful, and I'm not, again, I could give a whole lecture about that, but I'm not going to do that, is because it's very easy to derive all the PolyLog identities from this. Okay, if I say something wrong. Okay, so, good. Okay, so again, I just explained that for the purposes, the amplitude is a function of a geometric data, and a useful object to study these amplitudes is a symbol. So for example, for the example I gave you, you have a function, Li4, of some geometry. Now, if you start writing down the symbol using the properties I said, it will look like brackets and many terms. Okay, good. Okay, back to the amplitudes bootstrap program. So how do people like Dixon et al. Compute these amplitudes? So the way they're doing it is they start with some symbol alphabet. So it turns out only a certain number of letters contribute to these expressions. And then they impose certain constraints, and then they find unique solution. So for example, here is a chart from one of their papers. Again, this could be a whole topic of the talk. So they start with a certain, so this is just to give you proof that they've done it for very high loops. So this is the set of, this is how many functions you can, in principle, write for 6 points MHV and NMHV amplitudes. So then there was a whole interesting developments. What are the conditions that you can impose? It turns out something it's probably familiar to George very well. Steinman relations is something that's been known from the studies of old S matrix. Dramatically simplify. So that's some condition coming from physics. Dramatically simplify the set of functions that you need to look at. So they start with this set of functions, then they impose, various symmetry conditions, and until they can solve for the coefficients of these symbols. And so this is what's called amplitudes bootstrap, and they were able to, yeah.
0, 0 success.
Yeah. Yeah. So they satisfy Reggie limit, for example. So they played again. This is done with a computer and a lot of people and long, over a year each project. So because I think this was in this whole program. This number one was this was a crucial insight by actually Simon Caron-Huot. Because before they were just they were starting with actually Reggie, I think, from the very beginning. Okay, so and then they write down these expressions. Okay, I should also remark that these methods have been later also generalized for some QCD amplitude. So this is a very useful that turned to be a useful technique, and this has been done last year by Claude Dour and collaborators. Okay, but the thing to remember is this. So what is again the process? So one starts with symbol alphabet, one imposes constraints and finds the unique solution. Okay? So the question that I'm going to address in these two remaining parts of my talk is, how do you determine this symbol alphabet? So I'm not the one who goes and, given the alphabet, bootstraps. So for me, an interesting thing is, what do you know if nobody told you what the symbol alphabet? So for low points amplitudes, people derive this amplitudes by actually first by doing computations, by some other insight. But suppose nobody told you, how do you know and what are the properties of this symbol alphabet? Okay, so there are two interesting things I'm going to describe. Number one is that there's a connection between cluster algebra and symbol alphabet. And number two is that there's a connection between the symbol alphabet and Landau singularities. So these are completely two orthogonal things. So cluster algebra is something very well known to mathematicians. Landau singularities is something very well known to physicists. Like George, this is 60 years old, 60-year-old S-matrix program. So as a result, you get some cluster coordinates satisfying some Landau equations, which is, if nobody told you where this comes from, probably you wouldn't have guessed. Okay, symbol alphabet and cluster algebra. So two parts, symbol alphabet and cluster algebra. So how much cluster algebra should I explain here?
Explain us a little bit. We'll see by the reaction.
Okay, because okay. So the statement is this: is that so there are various statements in this field. So the statement that I'm going to make is that it is known that all evidence to date says that for all endpoint amplitudes, symbol alphabet is given by a subset of cluster coordinates on a Grassmannian.
Mm-hmm. So of those cluster algebras, those coordinate rings, Grassmannian for n, could you remind us which ones are finite?
Yeah, exactly. I will. Yeah. Yeah. So, well, I'll just 6 and 7 finite. Starting at 8, it's finite mutation, infinite number, and then starting at 9, infinite. Mm-hmm. So that's one of the reasons that a lot of this field has been focused on 6 and 7, precisely because it's a finite. Yeah. Okay, so. But
then it's finite. Then you say kind of
subset. That's also
would be still a subset.
Subset. Yeah, and I will try to explain that. Mm-hmm. Okay, so then do we need this slide here? I don't know. Yeah. Okay, so the simplest example of a cluster algebra is called A2 cluster algebra. So when you have, here, suppose we have two variables, A1 and A2. And we define a recursion relations, AN plus 1 is 1 plus AN over AN minus 1. So here, A1, A2, by this formula, A3 is 1 plus A2 over A1. A4 is 1 plus A3 over A2. If you do this plus 1, you get this. A5 is A4 plus 1 over A3. And now it turns out that it stops. So if you do 1 plus A5 divide by A4, you get back A1. So this is called a simplest A2 cluster algebra. So why A2? Because this is a Dynkin diagram for an A2. So more generally, you can define a cluster algebra by introducing a quiver. So suppose you have a quiver with nodes 1, 2, 3, 4, 5, 6, and some arrows between them. So given this quiver, we can encode this quiver by associating a matrix Bij, 6 by 6, because there's 6 nodes. And then the arrows are encoded in this matrix by this formula. Okay? So you're given a quiver and arrows between them. Okay? That's input. So the cluster algebra is defined by a set of all cluster coordinates produced by something called mutation out of this quiver. What is a mutation? So given this quiver, you can define a new cluster variable, A prime k, by this formula. Maybe we'll do this. Okay? So So given this, suppose I want to, I should also say to each node of the quiver you associate a variable. So we start with 6 variables, and then suppose we pick one of them, and we define a 2 prime, and we do the definition is that we mutate at node 2 by this formula. So we get something. I'm going to have an A2 example on the next slide. We get some new variable A2 prime, which is given by this formula, and we proceed doing this on each node and until, for example, you saw here it stopped. It was only 5 variables. Okay. So if we apply, is that okay? That's okay. No. So we have a quiver and arrows between them, and we have some rules, right? How to mutate by the formula, and we produce a list of coordinates. And that's called a cluster algebra, yeah? No. Yeah. Yes? Okay. Okay. So, good. For example, let's take this A2. We start with a quiver like this. You see arrow from 1 to 2. That's why, so for 1, it's like defined by, it's either 1s or -1, depends on the arrows. So the matrix B would be something like that. Yeah? So then we apply this formula. This is, so suppose I mutate at 1, at the node 1. So what happens is I apply this formula, so some B's, some A's, and I get this 1 plus A2 over A1. And this continues until we stop. So that's called A2. Okay? So, very good. So, okay. So now what do we need for the purposes of amplitudes? So there's something called Grassmannian cluster algebra. So to each GR for n, because I explained to you that the amplitudes live on this Grassmannian, there's something called the natural cluster algebra, or natural quiver to start with, is something called Grassmannian cluster algebra. Okay? So what you do, so this is the initial quiver, so you can open this paper, and the initial quiver is written there. Okay? You see these are the Plucker coordinates on P3. It's basically 3 by n minus 5 grid. So for example, momentarily we're going to do 6 and 7 points. Okay? So imagine this is the initial quiver, and then we start mutating using the rules, and we get the set of brackets. Which clearly, if you remember the symbol alphabet discussion, this is going to start looking very simple. So now this is a very busy slide. But let me just see. So suppose we have 6 points. So this is the quiver that we need to start with. This happens, so I told you it's 3 by n minus 5. So it's just 3, so it's A3. Now if you mutate them together, so for A2 we stopped at 5. Here you generate 14 quivers, and if you go through the list, you just mutate using these rules, you go through the list, you generate 15 coordinates, 15 of these brackets. Okay? And it turns out, okay, so there's also, I'm going to skip unnecessary details. So it turns out that these are exactly, part of them are exactly the arguments of these PolyLog functions. Okay? So thus, the main statement that I was trying to explain is that the symbol alphabet is a set of A coordinates. So these are called A coordinates, of 15 of them, and 15 you can get by, so there are 15 coordinates, and actually, for various purposes, it's 15 minus the number of points, so it's actually 9. So the symbol alphabet for 6 points would be 9 of these brackets. So, yeah.
So these are, in other words, these are all cluster variables which are not frozen.
Yes. Mm-hmm. Yeah. Yeah, this, I don't want to go for these, yeah, but since if you know, yeah, these are exactly, yeah, you can, yeah. Mm-hmm. Okay. So now, for example, you can take this 9, and that's what this is what people call in physics symbol alphabet. So they start with this 9, and then they build higher. So for 2 loops, so you have weight 4. functions. But then if you want to go to 3 loops, you start building these symbols out of these 9, but there are 6 tensor products. Okay, and then you start imposing conditions. Okay, but it's important. So this is the important observation. Okay, if you go to 7, the initial quiver will look like this. This is 3 by 3 by 2, and again, so this is more. So this was just a Stashev Politov for A3. So this becomes more complicated, and so but again, given this initial quiver and the set of mutation, you can produce the list of coordinates. So there will be 49 A coordinates in this many quivers. Again, so some details for the purpose of this talk are not as important. So we can make a choice, and the choice that people make, it could be shown that this quiver, by mutation, could be mapped to E6. So it's still finite dimensional cluster algebra. And the choice that people make is that this 49 admit 42. So 49 minus 7 is 42 homogeneous cross ratios. And these are the variables that people use in the bootstrap. So again, we take the set of A coordinates, and that's our symbol alphabet for the bootstrap.
What is the nature of the choice? You mean the choice of variables that other?
No, there's some. Yeah, some. I wrote this. Some papers use some other. I just wanted to fix this A's. Yeah, so that corresponds to this. Yeah.
But they're all equivalent.
Yeah, exactly. So the important thing is that this 42, and for odd n, actually, it is true that this could be these are the same if you set these nodes to 1, actually. So if you can see actually here, because if you look in this formula, these could be set to 1. Okay, so now what does this symbol alphabet look like? So for example, so I explained to you. For 6 points, you start with this 9, and then you have this tensor. So, for example, for 3 loops, weight 6. So, if you open paper by Dixon, Drummond, and Hen, it's actually becomes a Mathematica file. Okay, unfortunately, this becomes a Mathematica file. Well, unfortunately, so there will be so. Tensor 6 of these letters, the whole amplitude becomes something like this, and the key is there are lots of terms here. Okay, so if you go, for example, to 7.3 loops, okay, this was done in this paper. Again, a Mathematica file here. Okay, so
what does each term represent?
Each term is a symbol built out of these. So if you integrate it then back to the function, you'll have the function of these variables. Okay, so it's like a step between the actual function and so it's somewhere in between. Okay.
The function you have to take the 5-fold integral, right?
No, it's not an integral, it's a tensor product.
Yes, but to convert it to a function, so you...
Yeah, there's a whole process to how to convert it to the function. But this is useful because this tells you about the singularities of that function, for example. But and they actually, so for this case, they did write down the function. That's another step to go from this to the function, yeah.
So the minus and the plus encodes some information about the functions you get, or how?
Minus MHV?
Well, here, some terms seem to have minuses and others pluses.
Oh no, these are just coefficients. These are just coefficients in front of the symbol.
48. Oh.
Yeah. So this is the coefficient, and this is T means A11 tensor A11 tensor A11, etc. So there are all these. Just to give you an idea that you have the symbol alphabet, and there are tensor 6 product, and there are many terms. Okay, and they are there are papers where you can actually read these formulas. But but it would be nice to understand the structure of these, even though the functions are known. So one thing would be, just a second, would be to understand how you start with initial cluster, and maybe there's some path in the Stashev Politov which gives you an amplitude. That's a problem that, for example, we're currently thinking about. That's one of the problems we're thinking about. I'm going to say momentarily. Yeah.
Very question. So this is 3 loop amplitude?
Yeah.
So we're supposed to have 3 integrals? Or
Yeah, we are supposed to have six. Yeah, no. So this is I told you L loop is 2L, so that's why it's 6. This is nothing to. This is transcendentality, so that's at least 6. This is what it is. Yeah. So L corresponds to 2L. Yeah. So for example, 4 loops would be 8 tensor product, but there's nothing to do with.
So you mean this is the number of integrations in the integral formula for your PolyLog, and not?
Yes, it's precisely.
Yeah,
precisely.
That's why I was confused. So
Yeah, but it would be interesting to, of course, yeah.
should be consideration of the number of integrations.
Yeah, but that's not the way to think about it. Yeah, L corresponds to 2L. So, okay. Yeah.
When there is a belief that looking onto cluster algebras, you will actually get samples.
No. So it's an experimental fact. So somebody So somebody computed some amplitudes. So then we looked, even like 5 years ago with paper with Sasha, we looked at what the expression is and observed, this is very non-trivial observation, that the arguments in that expression are cluster coordinates. So that's when a non-trivial statement comes. Then we can now elaborate. We can take it, step further to use it for. So one of the things we're working on is trying to use this for higher loop amplitude. So take it as a given and try to.
On the lower loops, and it works.
It works exactly for all known examples. That's right. Are there questions? Is there a question?
So there is no way to understand how to derive system.
No, and in fact would be extremely interesting. But dual conformal symmetry in N equals 4 Yang-Mills, this is how it was observed. It was observed by Karchemsky and Sokachev by looking at the identity between 3 loop integrals. So, and then it was understood by others from ADS5. It was, that's.
So no justification from cutting and whatever.
No, absolutely not. I think it would be very interesting. No, 0. Okay. Any other question? That would be extremely interesting, but unfortunately. Okay. So an interesting thing would be to try to see if we can. So. One thing to think about, so we have some quivers, maybe there's some way to mutate by some rules and get the whole symbol. So a step in this direction, so the reason we started thinking about it, there was an interesting paper by James Drummond this October that analyzed the, so again, I explained to you that there exists expressions in the literature like that. So they observed that so we kind of want to fine-tune this statement now. So they observed that 2 coordinates appear next to each other in the symbol only if there exists a cluster where they both appear. Okay. So it works again. This worked for some examples up to 7 points, everything known, but there's no known reason where it's not known whether this is a physical or mathematical principle which requires this to be true or how general it is. So yeah.
So these things are symbols of iterated integral. And for those guys to be closed to give you a function, you have to take the bar differential on them.
Yeah.
So you need to know the cut product, and maybe that's the explanation.
Yeah.
This is likely to be the case. This is very likely to be the case. The problem is to compute the cut product. No, the problem is that if you take 2 arbitrary as functions and consider the corresponding element in K2, it's very hard to imagine the 0. And so if they're the same cluster, there is some kind of mechanism which explains why it could be 0. But this is it's very likely to be the case. I don't know whether anybody can make it 0 or something. But yes, that's probably.
That could be, yeah. Another thing I should mention, that this is actually a generalization of the Steinman relation, which is completely, it's discontinuity of discontinuity is 0. It turns out this is a more general way to think about so that's another thing they observed in the paper.
So,
I don't know what this is.
Okay.
Yeah, maybe.
The wonderful result of all the terms. Is this, where is n equal 4? Yes, I mean, is this for anything?
No, this is all A for n equals 4. That because the space of function that we work in is very particular. Number one. Number two, these brackets everywhere that we use also only for plain n equals 4. It's absolutely not the case for this momentum twist. The core is momentum twisters. This is only n equals 4. However, Han et al. Recently looked at some non-planar, some particular amplitude, also tried to take some symbol, but not built from these, and they were able to get something useful out of it. So
it's you make these cluster algebras, which you could do without ever thinking about quantum field theory, and then you find they have correspondence to.
Exactly.
So that's the point where the two.
Well, it's very non-trivial, absolutely, completely obscure. Yeah. No, that's the. Okay, good. Well, maybe I'll skip some. So, okay, some interesting possible things to work on. It certainly would be interesting to write this symbol in terms of some preferred clusters, maybe some paths in this stash of polytope, etc. And also, they looked at first thing we try to generalize is to look at, so they looked at 2 coordinates. So how about triples and quads? So this is a work in progress. Okay, there are other interesting applications of cluster algebras to amplitudes that I did not talk about. And so in some special kinematics, some other cluster algebras appear. They show up in the integrand, and they're also, so there's. This comes from some of our older work with Sasha. There are also constraints that they impose on the class of functions. So I've been focusing this talk on just symbol, not going to functions, but it turns out the functions are very constrained by requiring that these functions are only functions of certain cluster variables. Okay, so I'm switching to
just one more question about those clusters. How is it you spoke about finite alphabets, but if I understand correctly, starting from
8
and for 8, you said it's an infinite alphabet, but then does it make sense to do, what does it mean, bootstrap?
Yeah, okay. So to loop all n, Simon Caron-Hout computed the amplitude. So he has, for example, a subset of 108 letters that appear at 8 points. So one possible thing to do would be to start with this set of letters and bootstrap. But I don't think there's no understanding at the moment what that has to do. Yeah, there are subsets, but how to describe this mathematically, I don't think this is.
Because there's an infinite. We can probably agree. With an infinite alphabet, you cannot.
Yeah, you cannot go, but you can. Yeah, but if you just start with this 108, perhaps. Yeah. Okay, so second topic and last one is I'm going to describe the connection between the symbol alphabet and Landau singularity. So again, I'm going to be very, very schematic here. Okay, so so far, here's what I showed to you. I showed to you how to get the symbol from Bootstrap program, as opposed to as opposed to doing the integrals the way we usually do in quantum field theory. Okay, so number one, notice that it turns out that symbol captures the information about the singularity structure of the function. So now what we can go back to the integrand and see what we can learn from the integrand. Okay, so it is well known that given an integrand, the location of a singularity is described by Landau equations.
Are these points in the plane?
Yeah, just point. Yeah. Yeah. So thus, there could be a relation between the so the question would be there should be a close connection between solutions of Landau equations for this integral and the symbol alphabet. Okay, so we can do some experiments. So first, let me very schematically tell you what Landau equations are. So if you're given an integral, so perhaps with an example would be the best. So if you're given one loop 5-point integral like this, Landau equations tell you the location. So if you, without doing this integral, if you look at the Landau equations tell you about the location of these singularities. So what are the Landau equations? So equation number one is that all Okay, so I should have written. The way we do it in quantum field theory is we do Feynman parameterization in terms of these alpha parameters that are written here. And depending on how many alphas are set to 0, we call these leading or sub-leading, sub-sub-leading Landau singularities. So for example, the leading ones for this box, so equation number 1 is that all these internal momentas are on shell. So this is what it is. And number 2 is the something called Kirchhoff condition, that the sum of alpha I, QIs for all internal loops is 0. So just think about it. Here are the equations, okay? Given an integral, here are equations. And when do they admit solutions? Well, they admit solutions for alpha when the so these are 4 momenta. When the determinant built of 1, 2, 3, 4 is 0, okay? Well, where Q obeys this. So if you reorganize this, you get a condition that this should be 0. Okay, so this is the way to produce, out of an integral, to produce the location of the singularities of an integral. Okay, these equations. So okay. So if we move to more so that's an example. That's for each I. Each I is internal propagator.
So that way, some of the Q squares don't have to be M squared.
Yeah.
And
yeah. So for example, subleading would be alpha. So for example, subleading would be a triangle. So just forget about this condition. Set alpha 1 to 0, and then subleading would be a bubble. Okay. Okay. So these are the examples. So one thing we can, let me just show you back to our variables that we've been using. So for example, if you look at all possible boxes that appear in n equals to 4 Yang-Mills theory, and reparameterize external momenta in terms of these vector z's, you know that, so resolve these, the set of the leading Landau singularities will be given by the places where these brackets are 0. Okay, so these now are kind of starting to look like symbol entries, perhaps. Okay? So, okay, good. So these are boxes. So we can take as an example, so we can start by an example where we know the integrand. So for example, the one loop endpoint MHV, they could be written as a finite integral, something like pentagon integral like that. So we can solve, so given this integral, we can solve Landau equations. And we get the Landau singularities, which are written here. Okay, there's some brackets, some details about the brackets, bars, and various products. So these are details. Just the point is that given the integral, you can solve this. Now, we also know the answer for this integral. So this is some lead 2 of these. Again, I'm not giving you details of what the it's no point to do that in the talk. However, if we take the symbol, so we know the answer. If we take the symbol, we get only that these 2 letters appear. Okay? So we got a little bit too many from here. Okay? So we make this comparison, and we get a spurious Landau singularity. Okay, with this process. So there's not a one-to. It seems to be like there's not one-to-one map. So of course so that was an example. So we went on and reanalyzed all the higher, like 2-loop integrals where we know. So it turns out that all loop. So this again experiment. First experiment. All symbol entries are Landau singularities, and there are spurious Landau singularities that we produce that are not in symbol alphabet. Now, it could be not surprising because, these, whatever integral we start with normally can have numerators, for example. The numerators we don't take into account. Number 2 is we're summing the integrals, okay? So it could be that, when you sum, some singularities cancel. So then the question is how to eliminate these spurious singularities. So then comes the best inventions of 2013, amplituhedron. So I'm sure many of you heard from Nima. So I'm not going to go into great detail. I'm just going to tell you about this best invention. So the point is that it turns. So what does amplituhedron do? Amplituhedron tells you about the integrand to start with. So in principle, it tells you about the set of boundaries. So so it's a way to represent an integrand. Again, I'm going to skip a lot, but just give you an upshot. The integrand of an MHV amplitude is given by a certain form defined by having a log singularities only on the boundary of amplituhedron. So there's certain, okay, so this is external data, and the loop momenta, it turns out, could be written as a linear combination of some positive external data. So, so this is the procedure. So it turns out that the list, if we start with a list of boundaries in this object and apply this procedure, so we, again, maybe I should wrap it up. So essentially, the amplituhedron condition, roughly speaking, eliminates the spurious singularity. So there's some procedure. Again, this took a couple papers how to do this. So for example, at one loop, you have a boundary of one loop amplituhedron, a line going through I and J. This line could be obtained as a cut conditions of a box, which is like that. And then this box has Landau singularities given by these letters. So that kind of eliminates. So that's the whole. So we have the procedure which eliminates these spurious singularities, and this has been done so for two-loop MHV. There are some interesting results also for NMHV. There's some new refined definition of the amplituhedron. So one can go and use it now to make also predictions, because they're not. So that's in principle known for L, N, and K. So one can use this to go and predict the symbol alphabet from it. Okay. So some of the future directions. So this is so the direction this whole thing went to is to generalize it for NMHV and not only think about locations of branch points, but the whole generalization of this positive Grassmannian. So yeah, it would. So for NMHV, it's not quite clear what the cluster algebra story is. So there are some interesting work in progress on that. Okay, so I'm going to conclude. So on time. So I kind of sketched. So what did I do? I sketched for you this amplitude bootstrap program. So the important ingredients that enters, so the two things that one needs to do. One needs to know the symbol alphabet, and then one needs to know the set of conditions to impose on this alphabet to constrain the resulting amplitude. And then I explained to you the two interesting structures. Number one is that there is a connection between symbol alphabet and cluster algebra, and number two is there's a connection between symbol alphabet and Landau singularities. So I've done it for some examples, but many more questions remain. So I'll stop now.
Questions or comments?
It was perfect.
So in Landau equations, is parameters alpha with complex, or they should be within the simplex?
The other parameters and Feynman parameterization of an integral.
They're within the simplex.
Yeah. But yeah, these are standard when you do like QFT, first integral, the alpha. Yeah.
Yeah, but when you study the integral, if you do like make a period, you may want to deform the contours.
Yeah. No. Just we can, but
Start out.
You start with these. Yeah.
But for the equations. The position.
You have to find the solution within the boundaries.
Yeah, I mean the equations are just linear and alpha. So when do they exist? When determinant is 0. So when is this?
Delta complex.
Yeah.
I would expect the solutions would also have complex alphas.
But when does the solution exist? All we need to know from we're not really using much about. We don't need alpha. We need the constraints on external momenta. So when we want to know when the solution exists, so that's when determinant is 0. So, and that gives you the condition. So,
any
You
questions?
could find it.
Yeah.
How is it? I maybe haven't quite understood this Landau singularities. Could it possibly allow to narrow the alphabet in those infinite cases?
Yeah, that is exactly the point. Yeah, that is exactly the point. But it needs to be better understood. That is exactly the point. So yeah. Mm-hmm. Yeah, but again, from cluster algebra point of view, there's some cluster algebra in the integrand, and this is not very well understood, the connection between the two.
Any further questions? Thanks again.